So hello, Assalamualaikum and Selamat Sejahtera. So today our group 3 will be presenting Raman Spectroscopy. First of all, let's introduce our group member. So my name is Nur Yasmin binti Muhammad Ashir and my metric number is 201067. And
My name is Muhammad Amirul Fitri bin Tamizi and my metric number is 201057.
My name is Kirtana Ravindran and my matrix number is 201887.
My name is Nur Azmina and my metric number is 200827.
okay, next slide. Okay, so in this presentation, you guys actually will go through all these subtopics and you guys will be learning more about introduction of Raman spectroscopy, principle of Raman spectroscopy, the instrumentation, types, the difference between Raman spectroscopy and other methods, and application of Raman spectroscopy. Next slide. So for the introduction, what you guys need to know about Raman spectroscopy is Raman spectroscopy is a non-destructive chemical analysis technique which provide important detailed information such as chemical structure, crystallinity, molecular interaction, and phase. Uh, it is based upon the interaction of light with the chemical bond within a material. So Raman is basically a light scattering technique whereby a molecule scatters incident light from a high intensity lasers light source. As you can see in the picture shows a basic information on how Raman spectroscopy works. It started with a laser light hitting a sample, for example, such as powder, solution, metal, ceramic, or even a tissue, and the lights will be emitted back from the sample and dispersed into a multiple color and goes through the filter. So this filter will remove the laser wavelength and goes through dispersed spectrometer, and lastly will reach the detector and transmitted into the computer, producing data in a form of graph. So next slide. So next is a Raman shift calculation formulas. There are four different formulas to calculate, which is the first one is to calculate the Raman shift. Second one to calculate the Raman resolution. The third one to calculate the wavelength. And the last one is to calculate the wavelength resolution. Next slide. So, okay, moving on to the principle. The principle of Raman spectroscopy actually tells us there are two types of scattering light. So, which is Rayleigh scattering and Raman effect. So, for the Rayleigh scattering, or called as elastic scattering, this happens actually when lights interact with the molecule in a gas, liquid, or solid. The vast majority of the photon are dispersed or scattered at the same energy as in the incident photos. As you can see from the picture, that shows that same energy levels. So for the Raman effect, this Raman effect tells us that a small number of these photons, approximately one photon in 10 million, will scatter at a different frequency than the incident photons. So next slide.
So moving on to the instrumentation, this is the schematic diagram for the Raman spectroscopy, which is known as Raman spectrometer. So in this diagram, we have shown laser, which is the source of our light, and then the beam splitter that is used to divide the beams into two or more beams with different plugs. And then the focusing lens is used to focus or latch on the beam's laser. Then the notch filter is it only allows a certain or specific range of wavelengths that can pass through it. And then the spectrometer is to measure the wavelength of the light, and then the last one is the CCD, also known as the charge couple device that used to convert the lights into electrical signal. Then next slide. This is the components of the Raman spectroscopy as stated just now. The laser to emit the light of narrow bandwidth through optical amplification, then the CCD to convert the light into electrical signal, the lens that use to focus or disperse an optical beam, the filter that is to transmit or reject a specific range of wavelength, the beam splitter that divides the incident beam into two or more beams of different flux, and then the spectrometer that take in the light and then break into its spectral components, then read it out and display through a computer, and also the microscope objective that acquire the spectrum to the sample. So in Raman spectroscopy, we have three sample illumination system, which is the solid samples, liquid samples, and gas samples. In solid samples, actually it is acquired by filling small cavity with the same sample after it has been ground to a fine powder. However, polymers can directly be analyzed without the sample pre-treatment. Meanwhile, for the liquid samples, water is a weak Raman scatter but a strong absorber in infrared radiation, so most suitable by using Raman spectroscopy. And the last one is the gas sample that is normally contained in glass tubes and also can be sealed in a small capillary tubes. So this is the Raman spectra. As can see, there is two types of wavelength, which is the blue one and then the red one. This is because the spectra are different due to their different phase and crystalline structure. Then the Raman shape is the difference in frequency between the laser light and scattered light. The count rate is the quantity of events the spectrometer defects for the particular Raman shift per second and is relative to the strength of the light detected. So these are the other two Raman spectra, and for the for example, this colorless, clear colorless liquid in glass container. Actually, the bands in the spectra are related to molecular structure, and each molecule has a very specific overall pattern that can be matched to spectra of non-standards. Or in other words, it can be said that in Raman spectroscopy, we also have a table of frequency for the functional groups. Then actually, as you guys can see, we have three spectra in the graph, which is the, after being analyzed, we can see that there is acetonitrile, cyclohexane, and then the chloroform mixture, chloroform or chloropicrin mixture. So the acetonitrile actually contains a cyanide linkage that we can see that it shows up here the 2250 centimeter power to negative 1. So this band is very specific for cyanide and can be easily used to identify other cyanide containing unknowns. Then the lower spectrum shows a mixture of chlorinated compound. So we can see that the bands at the lower frequency, which is below the 500. Then the middle one shows a pure hydrocarbon solvent, which we can see that the bands is in the middle region.
Video is the animation about Raman spectroscopy. The Raman spectroscopy was named after one of its discoverers, the Indian scientist known as C.V. Raman, who observed the changes in wavelength due to the deflected light when it interacts with a transparent substance. This scattering light is known as Raman effect, and its discovery paved the way for modern Raman spectroscopy. The Raman microscope is widely used by mineralogists and geochemists to identify the minerals and biological materials that are present in a sample. The microscope is equipped with a laser that will help to identify the crystals on the slide. Inside the crystals, the photons from the laser interact with molecules, causing them to vibrate. Then the change in wavelength from the initial laser to the wavelength of energy emitted from the vibrating bonds between the atoms will reveal the contents of the sample. Next, the emitted energy passes through a spectrograph which divides it into a spectrum of light. A CCD detector will be used to analyze the spectrum and converts it into electrical signal. The peaks in the Raman spectrum represent the different vibrations in the crystal's molecular bonds. This is because each mineral has its own unique spectral fingerprint. Thus, Raman spectroscopy is used to identify minerals here on Earth, such as aragonite, and also minerals on the other planets, like Mars. In this second video, we'll show you the technique when using Raman microscope. The sample used in this experiment is an aspirin. The sample was put on a slide before loaded onto a sample holder. Then the slide is pushed to the end so that it can be clamped by a steel clamp. Also, in this experiment, a software called Lab Spec 6 is used. Then the video mode was chosen. The joystick was used to focus on the sample and at the same time also check on the computer screen. As you can see, there are several crystals with different sizes and shapes. Then, one of the crystals was selected. For the measurement, long working distance objective will be used and adjust the gain on the sample. On the right hand side of the Lab Spec 6 interface, you can choose the Acquisition tab to manage acquisition setting. This allows you to type in spectral range you want to scan or accumulation numbers to repeat the acquisitions, and also shows the time to wait before the data acquisition is obtained. This is the Raman spectrum of aspirin obtained in just 0.5 seconds. As we can see, the Raman bands are narrow.
So now we are going to discuss on the types of Raman spectroscopy. We have 4 types, which is the resonance Raman spectroscopy, surface enhanced Raman spectroscopy, micro Raman spectroscopy, non-linear Raman spectroscopy. So next slide. So what are the advantages when you use Raman spectroscopy? This is because when you use Raman spectroscopy to check on the samples, they offer you very detailed sample characterizing by providing individual chemical bond vibration. Another reason is because Raman spectroscopy also offers the analyst high sensitivity microscope analysis with submicron spectral resolutions. Another reason is because that Raman spectroscopy also probes more subtle chemical effects such as crystallinity, polymorphism, phase, intrinsic stress and strains. protein folding, and hydrogen bonding. Lastly, Raman spectroscopy is a very fast technique, typically requiring just a few seconds to obtain a good quality spectrum. So continuing, so differences. We do know that generally they have a lot of type of spectroscopy in the analytic method. So the differences between Raman spectroscopy and infrared spectroscopy is the the formation of the lights, which is Raman, is due to the scattering of light by vibration, while infrared is absorption of light by vibration. So next is the changes happens in sorry. So the secondly is the changes in the polarizability, while infrared has the changes happens in the dipole moment. Raman spectroscopy gives a symmetrical vibration, while infrared shows an asymmetrical vibration. So Raman spectroscopy shows a momentary distortion of the electrons around the bond, while infrared shows excitation of molecule to the excited vibrational state. So the solvent in Raman spectroscopy is water, while infrared do not use water, while they use organic solvent. Uh, Lastly is Raman spectroscopy indicates of the covalent characters in the molecules, while infrared also does this in indication of character, but it's more of an ionic character for the molecules. So next we're going to compare Raman spectroscopy and electron spectroscopy. In Raman spectroscopy, there is no requirement of sample preparation, while electron spectroscopy does. Uh, to compare which is better and which is easier to be handled, which Raman spectroscopy takes it because it is easier to handle the environment condition where there is no heat or no vacuum and relative humidity, while electron spectroscopy is harder to control those environments condition. The time taken for analysis in Raman spectroscopy is faster compared to electron because it's less than 10 minutes. Also that we know that Raman spectroscopy can measure multi-layer samples rather than single layer, while electron spectroscopy only does single layer. So next is Raman spectroscopy and X-ray powder diffraction spectroscopy. Raman spectroscopy measures crystalline and amorphous materials, while X-ray powder doesn't. Raman spectroscopy also does single particle analysis, which is possible. It is easier to handle the environment condition just like before. But in X-ray powder diffraction spectroscopy does not does the same thing because it is harder to control. The bench footprint is smaller compared to X-ray powder diffraction, which is bigger. So next is, so this is the comparison of infrared and Raman spectra. So as you can see in Raman microscopy, they often goes to like uh, the comparisons with the gold standard spectroscopic technique for molecules, namely Fourier transform infrared spectroscopy, which is a specific way of infrared spectroscopy. But this kind of techniques are better treated as complementing each other rather than alternatives.
So next, the application of Raman spectroscopy. So for Raman spectroscopy, there are many uses for narcotic, for pharmaceutical, and medical and also chemically can use to detect anything. So why is Raman spectroscopy is applied? First is because all fields that require close proximity identification between inspecting tools qualitatively, then lesser technical issue, then is easily identify chemical structure used for fingerprint technique, then little or simple preparation required. Next, non-invasive and also non-destructive method. So it can be used many times. So quantitatively, resonance Raman spectroscopy allow detection of 10 negative 3 to 10 negative 7 by using laser light with wavelength approaching electronic absorption. Uh, then surface enhanced Raman spectroscopy places samples on metal or rough surface that increase Raman scattering. Next, Raman spectroscopy application for incoming good inspection, spectral database comparison to a pre-selected spectrum in the library is used. So it can verify the ingredient. So if we don't know what ingredient we are using or what chemical, so we can use Raman spectroscopy to inspect. And then other than that, can prevent from being used, means that uh, when the chemical or the solution that is harmful or hazardous, we can prevent it from being used. Then measure through packaging, so we can measure the quantity and the amount of the chemical or the solution or the material from just outside the object. So we don't need to to open the material or anything. And then to detect poor qualities. Next, hazardous material identification. We can evaluate whether the substance are hazardous or harmless. And then the first responder, like the narcotic or like medical use. So the first response, or so for other than that, for like chemists, so the first responder will be safe in a safe working situation. So for example, like so they use Raman spectrometer to detect the substance in the white substance that may be hazardous to the responder. So they can prevent that from the first responder to be harmful. So next application is reaction monitoring. Monitor the reaction of an epoxy hardening in situ, means for chemical and pharmaceutical production, they can save money and also time, save money and their time, because this Raman spectroscopy is thermal and chemical resistant. Then scattered light is collected with a fiber probe head, means they place in a chamber, and then the Raman spectrometer will detect the detect the substance within not long time. So they can monitor the chemical conversion of one substance into another. Like for example, in the graph provided, there are multiple of substances that are being tested. So the color of the graph is from dark red to light red. The the result is from 200 until 1,400 reaction, and then the signal in the Raman spectrometer is increasing due to the reason. So that's all from us. If you have any question, you can ask. Thank you.